You know, 3D printing was supposed to change everything, right? Let us create almost anything we could imagine. But for the really tough jobs, parts in cars, planes, or even inside the human body, plastic just hasn't been strong enough. It couldn't replace metal. Well, what if that's all about to change? So think about this for a second. What if you could use a regular, off-the-shelf 3D printer to make parts that are way, way stronger than anything it's made before? This isn't just a fun thought experiment. It's the big question driving some really fascinating new research. And we might just have an answer. It comes from a 2024 paper in the Journal of Applied Polymer Science. Researchers from the Federal University of São Carlos in Brazil published a work called, and get ready for this, continuous glass fiber reinforced polycaprolactam composite produced in a conventional fused filament fabrication equipment, process modeling, and parameters adjustment. Okay, it's a mouthful, I know, but this little diagram from their paper basically gives us the roadmap for this whole explainer. First, they had to create a totally new kind of filament. Then, they had to figure out the crazy physics of printing it. And finally, they had to dial everything in to make it actually work. So, how do you make plastic stronger? Well, it's the same idea as making concrete stronger. You reinforce it. But instead of using steel rebar like in a skyscraper, the idea here is to embed a continuous bundle of incredibly strong glass fibers right inside the plastic filament. Now, you can't just dump some fibers into a bucket of plastic and mix it up. They had to come up with something way more clever. They engineered the special tool called a crosshead die. You see, the bundle of fibers goes in from the left, and then hot, melted plastic, in this case a biodegradable polymer called PCl, gets shot in from the top. It perfectly coats the fibers as they pass right through the middle. The whole process is this elegant three-step dance. You feed the fiber in, you coat it with hot plastic, and then you just pull it out the other side, letting it cool into a standard-sized filament that any desktop 3D printer can use. Sounds pretty straightforward, right? Well, as they were about to find out, making the filament was actually the easy part. The moment they cut open their brand new filament and put it under a microscope, they saw a big problem. See that dense cluster of fibers right in the center? The plastic is really just a jacket on the outside. It hasn't fully soaked in or impregnated the bundle, and that's a huge weakness. If the fibers and the plastic aren't bonded together, the fibers can't really lend their strength to the final part. So that was problem number one. But when they actually tried to print with this new stuff, things got even worse. The whole process was just unstable. To figure out why, the researchers had to put on their physicist hats and model all the invisible forces happening inside the tiny nozzle of that 3D printer. And this is where things get really smart. They realized that their problem, a solid core moving through molten stuff in a tight space, is actually a lot like how we make coated electrical wires. So they just adapted a fluid dynamics model from that industry, basically treating the fiber bundle as a moving wire and the printer nozzle as the outer coating die. And wow, did their models show something interesting? On the left, that's what the flow of normal, boring PCl plastic looks like. It's a nice, smooth, predictable curve. But on the right, that's what happens when you shove the fiber bundle in there. The flow gets totally distorted. The solid core blocks the middle, forcing all that molten plastic into a really narrow channel and creating some pretty extreme conditions. The biggest takeaway from their model was all about pressure. That fiber bundle more than doubles the pressure gradient. And that's just a fancy way of saying the printer has to push way, way harder to squeeze this new material out of the nozzle. This insane pressure creates another issue, extreme shear. Now, shear is kind of like internal friction in a liquid. Think about honey. Letting it ooze slowly is low shear, but trying to squeeze it through a tiny pinhole at high speed, that's high shear. And the model predicted shear rates almost 4 times higher with the fibers. This makes the flow really unstable and turbulent, which finally explained why their first prints were such a mess. Okay, so now they knew why everything was going wrong. They understood the physics, so they could shift from theory back to practice. It was time to figure out how to tame this high-pressure, high-shear flow. Time for some good old-fashioned scientific trial and error. And this table right here just shows you the incredible amount of work they did. They tested everything. I mean, look at specimen 1 up there in the top left. They printed it too hot with a small nozzle, and it's just a wavy, inconsistent disaster. But they kept at it, changing one thing at a time, documenting every single result until, bam, they got to specimen 10. Look at that, straight, consistent, beautiful lines. They had finally found the secret recipe. And that secret recipe wasn't just one magic bullet. It was a very precise combination. They needed a bigger nozzle, 1 millimeter, to lower the pressure. They needed a very specific temperature, 95 degrees Celsius, to get the plastic flowing just right. And they had to slow the whole print speed way down to keep everything stable and controlled. So after all that work, inventing a new material, modeling all that complex physics, running dozens and dozens of experiments, what did they actually get? And maybe more importantly, where does this kind of technology go from here? All right, here's the side-by-side comparison. On the left, that's a grid printed with standard plastic. It's clean, it's precise. On the right is their final fiber-reinforced print. You can see it's a bit rougher around the edges, not quite as perfect. But you have to understand, this is not a failure. This is a massive success. It's the proof of concept. They proved it can actually be done. Of course, the tech isn't perfect yet. Not by a long shot. That initial problem of the plastic not fully soaking into the fibers is still there. You can see how the fiber bundle can still pull away from the plastic. Improving that bond, that's the next big challenge to really unlock this material's full strength. So, why does all of this matter? Well, for one, it opens a door to printing high-strength parts on regular, affordable 3D printers. That could be huge for industries like aerospace or automotive, which are always looking for strong but lightweight parts. But the most exciting part, the real game changer, is the plastic they chose to use. PCL isn't just any plastic. It's biodegradable and biocompatible, and that opens the door to something truly incredible, printing custom medical implants. What they could print is something called a tissue engineering scaffold. So what is that? Well, imagine a 3D printed lattice that you can implant in the body. It acts like a temporary framework or a jungle gym for your own cells. It gives them support and encourages them to grow in and regenerate damaged bone or cartilage. And the best part? As your body heals, the PCL scaffold just slowly and safely dissolves away, leaving only your own new tissue behind. This research really is a step toward a future where a surgeon could scan an injury, design a custom reinforced implant right there, and print it in the hospital with a simple desktop machine. It makes you wonder, right? Could we be heading toward a future where rebuilding parts of our own bodies is as simple as clicking print?